Okay. I know that you might not be done, but I want to hear the transformations you came up with. Okay, Paula, give me one of our transformations. Okay, so there's a horizontal translation. And plus 3, does that mean to the right 3 or left 3? Thank you. So to the right 3 units. Perfect. That is the only horizontal transformation because that is the only thing that is happening inside of what's being squared. Everything else should be discussed as some sort of vertical transformation because it's happening after the squaring is done. Samir? Okay, so there's a vertical translation, and it's going down 5. All right. Ooh, look at all the hands. Max.
Vertical compression by factor of 1/2.
Good. Okay, vertical compression by a factor of 1/2. Good job. Yes, Will. Good. But remember, it's always x minus h in the formula. So it looks like minus 3, but you would really, the minus is part of the formula. So the number after the minus is a positive 3, and it's a right 3 movement. Okay? No. It's for everything. That's why we wrote it on the back of your transformations of f of x minus h. It didn't have to be in absolute value bars. It could be in anything. Okay? Malia. Okay, good. So what's the difference between a horizontal stretch and a vertical compression? Visually, they do the same thing. They both tend to make the graph like wider, say, okay, because you're vertically compressing or horizontally stretching. However, this number is not inside of the perfect square. And if it was inside of the perfect square, it might be a whole different number because you can't just throw a 1/2 in there when that parentheses was being squared because order of operations would make you do the squaring before the 1/2. So I would actually have to do a lot of mathematical work to rewrite this with the 1/2 inside of there to see what number it ends up turning into or how it affects the other thing to call it a horizontal change. So even though there's a vertical compression, it will look the same as a horizontal stretch, but maybe not by the same amount. Like just because our vertical compression is by a factor of 1/2, it doesn't mean that it's necessarily a horizontal stretch by a factor of 2. Okay, and I'll show you as we go through how to graph it, why you want to know the difference between if it's vertical or horizontal, on how to get the points in the right place on the graph. Okay? All right. So when you're graphing using transformations, the equations have to be set up in this form where kind of everything's nicely packaged inside of whatever it is, a radical, a square, an absolute value, and then you can see the stuff outside of it. If it's not written like that, then you wouldn't be able to identify the transformations. Okay? So this is nicely written like that. We can identify the transformations. When you want to graph with transformations, you start with the parent function. So think about what our graph of f of x equals x squared looks like. I'm going to put that on here. So you guys have a couple of choices. We're going to graph every step, okay, on this graph. I'm going to graph in different colors as I go. You can graph in different colors as you go. You can graph it really lightly and just kind of number the steps so you could follow it later and then make the final one darker so you can see the difference. Or if you want, okay, you could get out a separate sheet of paper and you could graph each step that we do separately and then just put the final graph on this graph if you want to. Does that make sense to everybody? Because there's going to be a few steps because we're going through all the transformations. Now, as we're doing this, you might think, I can graph parabolas faster than doing all these transformations, and you might be right. But this method is not going to just show up in this unit. It's going to show up in the next unit, the next unit, the next unit, the next unit. So it would benefit you to learn how to use the transformations correctly. Okay? Samir, question? Okay. All right. So I'm going to graph the parent function in yellow. I know that's not going to be the best to see, but that's kind of like, maybe I'll get darker as I go so we can see each step a little bit better. So the parent function has a vertex at 0, 0, because when you plug in 0 for x, you get 0 for y. When you plug in 1, you get 1. So it has the point 1, 1 and negative 1, 1. And when you plug in 2, you get 4. Now, we are eventually going to have this parent function memorized. We're going to be like, oh, x squared, parabola, 0, 0, over 1, up 1, over 2, up 4. We're going to know where those points are. Okay? So vertex is important and a couple of points around it. So this is my parent function. Okay? Sorry, I can't draw straight. What do you mean, why did I go up? What do you mean, why did I go up?
You want like the slope of 1, 1, and then you change your slope.
This isn't slope. Are these straight lines? No, it's a parabola. When you plug in 1 and you square it, you get 1. But when you plug in 2 and square it, what do you get? 4. Okay? So this is our parent function. On Monday, we will put this on a door, just like we did with the absolute value function. Okay? Yes? When I plug in 0, I get 0. When I plug in 1, I get 1. And when I plug in negative 1, I get 1. And when I say plug in, I'm just plugging in an x, calculating it, and see what I get as the y value. Okay? Because you square it. So when you plug it in, it's going to turn positive. What?
No matter what.
Yeah, if you square a number, whether it's positive or negative, it ends up being positive. Okay, now that that's questions answered, your eyes should be up here. You can turn later and talk to your group when that's the case, but you should be focusing on being able to do this up here. Okay, so first transformation, a horizontal translation of right 3. Okay, part of the reason we're doing all of these separately, you're not going to be asked to do all of these at once in the homework all the time. Some of the problems have 3, 4 transformations. Some of them just have 1. So I want you to see how to do every type of transformation. As you get better at doing these, you'll learn what you're comfortable with, which ones you have to do separately, and which ones you feel like you can do together. So we're going to move everything to the right 3. The whole graph is going to get shifted to the right 3. So everyone should be redrawing their graph to the right 3. I'm just going to put a little number 1 next to it so you know that that's what I got after I did the first transformation. Okay, so I'm trying to match my graph with what I numbered over there. Okay. So I took the whole graph, the parent function, I moved every point to the right 3 because that's what it said to do for the transformation. Horizontal translation, right 3. Okay. The next transformation we listed is a vertical translation down 5. I'm now going to take every point, not from the parent function, but from where I am now, and move everything down 5. Okay? No. The only thing that matters, so listen closely to this, you can do the transformations in any order. In class, to be consistent, I will do all the horizontal ones and then all the vertical ones. As a teacher, it just helps me make sure you build a good understanding of which ones are horizontal and which ones are vertical. So I like to do that in class. Also, I will do a reflection. Like if there's a horizontal reflection, I need to do that before I do a horizontal shift. Because think about it. If I reflect and then shift to the left, my graph is supposed to be over here. But if I had shifted to the left and then I did the reflection, my graph would end up in the wrong place. So the only rule about the order of the transformations is that if there's a horizontal reflection, you should do that before any sort of horizontal shifting. If there's a vertical reflection, you should do that before you shift anything vertically, okay? So for me, I'm going to make a horizontal list and a vertical list. If there's any sort of reflection, they're going to be at the top of their list. So if there's a horizontal reflection, I'll have it at the top of my horizontal list. And if there's a vertical reflection, I'll have it at the top of my vertical list. Okay? All right, the last thing I'm going to do. So here's the thing that gets a little bit tricky. Vertical compression by a factor of 1/2. In order to compress or stretch something, they must be getting compressed or stretched towards something. Okay? So there is a point of reference that we use, and for all of these functions that we're starting out with, the vertex is the point of reference. That point is not going to move, and things stretch or compress towards or away from that point, horizontally or vertically. Okay? Here's how you perform stretches or compressions. Look at a point that's surrounding that point. Okay? How far is this point that I circled from the vertex horizontally? So I'm only looking at one direction here. 1 unit. Is that going to change? Is there any horizontal stretching or compressing going on? No. So there is still going to be a point that is 1 unit to the right of the vertex point. What's going to change is how far it is vertically because we have a vertical compression. Okay? How far is the point that I circled from the vertex vertically? So currently, it's 1 unit away. Literally, you have written here what to do. We basically need to multiply by a factor of 1/2. The distance is getting changed by a multiple of 1/2. So I'm going to take what was the distance, 1. I'm going to multiply that by 1/2. What's 1 times 1/2? 1/2. That is the new distance. That point that I was at needs to be located so that it is 1/2 a unit from the vertex vertically. So it will no longer be here. It will be like right here. And its mirror image would be over here. So I'm taking a vertical distance of how far a point is from the vertex. I'm multiplying it by whatever my vertical stretch or compression is saying. I have a new distance, and that's how far I now put the point. But all vertically because we're not talking horizontal stretch and compression. Okay? So this other point over here. Okay? How far is this point from the vertex point horizontally? 2 units. Is that going to change? No. How far is that point from the vertex point vertically? 4. Okay. So it's a distance of 4. 4 is going to get multiplied by 1/2, and 4 times 1/2 is 2. This point needs to be moved so that it will be a distance of 2 units vertically from the vertex point. So rather than up here 4 units away, here's where the level of the vertex point was, 1, 2. It should only be 2 units above it. And its mirror image over here. I'm going to draw the graph now, and we should be able to see that we did the right transformation. Okay, so the blue one is my final graph. Look at the one that was right before the blue one, so the orange graph up here, and look at the blue one. Does it look like we did what we said was supposed to happen? Does it look like a vertical compression occurred? Did the graph get pushed outward like that? Then we probably did the right thing as long as we did the arithmetic right. Okay? So do you get how to graph with transformations, at least a little bit, getting our feet wet a little bit, okay? Can list them all, and step by step we can go through them. All right, so now these questions. What is the vertex of our parabola? No. 3, -5. Now, well, we'll talk about how it was written later when we look at the PowerPoint. But you can actually tell from the equation that you should have got a vertex of 3, -5. So we did, well, yeah, H and K. Good job. Okay, what is the axis of symmetry for this parabola? Yeah, Matt? Good. X equals 3. Because it's going to be a vertical line going down through the vertex. Okay, vertical lines have the equation x equals and whatever number you know they're going through. What is the minimum point of the graph? For this part, you can just list the whole point, but I like what you're thinking. So this is actually why I put this question up here. This becomes a really big deal in pre-calc, and then when we look at data too. So remember when we were doing data, you had to always interpret not just the number, but like what it was telling you, right? So maybe like the way that this is shaped, you're saying, oh, it reaches -5. Maybe this is, I don't know, stock market decrease or increase of something over an amount of years, and I'm saying, oh, over 3 years, it reached a decrease of -5, something like that. That's where it's going to become important too. So generally when they ask just for minimum in general, you can list a point. But if they ask for the minimum value, it's exactly what Samir was saying. They really just want to know what is that lowest value that it's reaching, and you would say that's -5. If they ask where the minimum occurs, they're usually asking which x value goes with that, so 3. So we'll use that a little bit when we look at data in this unit, and it's important in pre-calc, okay? All right. Domain. What is the domain of our function? Joshua? No. So remember the domain is what are the x values that are okay to plug in? Great? Good. All real numbers. Okay, so remember across the x-axis, this has no stopping left or right, so it's going to go forever. So there's no limitation on the x's. Or we could say from -infinity to infinity. What about the range of this graph when we're thinking about the y values?
Y is greater than or equal to -5.
Good. Y is greater than or equal to -5. So it's above or at -5. -5 is the minimum. It goes infinitely upward. We would have that bracket at -5 if we wrote it that way. Okay. All right. So we're going to try one more like this so we can see some more transformations. No, one or the other. But we're just going to, whenever we're doing it in class, we'll do both so that people can eventually catch on to what both mean. Okay? All right. Second example. All right. List for me the transformation. So as a class, again, I'm not going to be picky how you do it individually, but just to keep us organized as a class, let's focus first on horizontal, and in each category, if there's a reflection, we'll put that first. So the first question, is there a horizontal reflection? Horizontal reflection would be multiplication by a negative, but inside of the square. Is x being multiplied by a negative? No. So I don't have a horizontal reflection. Now I can go list any of my other horizontal transformations. Okay? What are my horizontal transformations here? Okay, so we have a horizontal translation left 5. Okay, so that's what we'll do first. All right, now let's talk about our vertical stuff. And in this list, again, if there's a vertical reflection, we want to list that first so we don't accidentally shift and then flip it over to the other side of the graph where it's not supposed to be. Okay, good, but I want to list if there's a reflection first. Is there a reflection? Yes. How do I know? Because of the negative in front of the 3. So I'm going to list the vertical reflection, and then Samir, what was it that you said? Okay, so it goes up 2. So I have a vertical reflection. I have a vertical translation up 2. Okay. What else? Jordan? Okay, good. A vertical stretch. And I just have to say by a factor of 3. Yeah, how come I don't have to mention the negative part of it? Matt? Good, I already reflected it. So because we refer to that as a different translation, we don't need to say it again. So it'll be a vertical stretch by a factor of 3. Okay, so on your graph, plot your parent function first, okay? Yes?
For the vertical stretch by factor of 3,
Uh-huh.
just from the negative.
Yes. Oops, sorry. My like parabola lines are just like really ugly today. I apologize. My curves, I guess. My pen's like slipping, sliding. I'm just not doing a good job. All right, so here's my parent function. Okay? So remember, the parent function is going to be the same as it was last time for anything that's squared. So first thing, take our graph, move it left 5. Okay? Rebuild it. Okay? That was it. So we went to the left 5. The next thing I'm going to do is I'm going to perform a vertical reflection. What happens when you do a vertical reflection? Fletcher? Flips it down. So vertical means stuff from up to down. So remember, when you're reflecting or compressing or stretching, normally this vertex point is going to remain unchanged. But like this used to be up at +1, now it's going to be down at -1. It's only the vertical stuff that's changing. You're not changing anything left and right, just up and down. Okay? So these points will be in the same type of location, but below the axis instead of above. Okay? So that's my reflection. Then I'm going to go with this vertical translation up 2. So I'm going to take every point on my graph, and I'm going to move it up 2 units. everybody okay where we are here? Because then we'll take a little extra time with the stretching, compressing part, because that tends to be a little more difficult. Is everybody good to hear? Any questions? All right, I'm going to actually erase the background graphs now just so you can pay attention up here to stretching and compressing, because some of the writing will go over this other stuff. You can make all the background stuff. Yes? I'm not erasing the red one that you're making right now. Can I erase the other ones? All right. So the last thing I'm going to do is a vertical stretch by a factor of 3. What am I stretching away from? What am I measuring all the distances from? The vertex. Got to know that so I understand that that point stays the same. What distances are going to be changing, horizontally or vertically? Vertically, okay? So there's still going to be a point that I'm going to plot a unit away from here, but it's going to be about where it is. And since it's a stretch, I expect this to be moved further away from the vertex, okay? Specifically by our factor of 3. So I'm going to measure the current distance, multiply it by 3, and plot the new point that's that far away. So right now, that point vertically is 1 unit away from the vertex. I'm going to multiply that by 3, which means when I plot it for my final graph, I want the point to be 3 units from the vertex. Now, let me be clear. Not 3 more units away from where it is right now, that the total distance between the point and the vertex vertically should be 3. So the vertex is here. 1, 2, 3. It should be here. Okay, and it's a mirror image. Okay. This point down here. Okay. How far is it vertically? 4. I'm going to times that by 3, which is going to give me a new distance of 12. Not 12 more than where it was right here. I'm going to plot a point that is 12 units vertically away from the vertex. So here's the vertex level. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and it's mirror image over here. Okay. And again, if we did it pretty much right, I mean, maybe you might mess up the arithmetic here and there with the numbers, but it should look like we performed what we wrote down. From the red graph to the blue graph, does it look like there was a vertical stretch? Okay, yeah, so it looks like I did the right thing, okay? So that looks good. All right, what is our vertex for this parabola? -5, 2, good. Somebody else, raise your hand, give me the axis of symmetry. Jordan. Good. Somebody else, can you tell me what the minimum of the graph is? No? No? Ashley? Okay, so kind of. It doesn't have one, right? When we denote it with domain and range, we use negative to infinity to say, oh, it goes forever. So this doesn't have a minimum. We wouldn't be able to answer this question about this graph. What does this graph have that the other one didn't? A maximum. So if they want to ask us something more specific, they would ask us about a maximum point. What is the domain of this graph? Somebody raise your hand and tell me. Yeah, Emily? Good. All real numbers. Okay. Or from negative infinity to infinity. All right. What is the range of the graph? Vivian? Okay, so any number less than 2? So we would say y is less than or equal to 2. Okay? And so if we did it with interval notation, it would say that our graph goes from negative infinity to 2, a bracket at 2, and a parentheses at negative infinity. Okay? All right, so I know that last night's homework was tough, but it's worth the struggle to try and understand the transformations. Tonight's homework might actually be simpler because it's about transformations of one kind of equation rather than like all the different ones at once. So all of your problems are going to be problems like this. This is kind of the hardest they'll get as far as number of transformations. Like one of the problems will just be this, x plus 5 squared, and you have one transformation to do. Or x squared plus 2. or 3x squared. And then towards the end, they'll do ones like this that have 2 or 3 or 4 transformations. Okay? Yes. All the quadratics, so anything that has this squared in it, would use this same parent function because they're all in that family of quadratics. Okay? Yeah. Josh? Parabolas, yeah. Okay. Let me stop this. This is good.